Dear learners, during the last sessions on complex variables, we have talked enough about analytic functions in Cartesian as well as in polar form. In this session, we'll be concentrating on the concept of transformations. We have been using the word transformation so many times till now. As far as M3 is concerned, we have already talked about Z transformation, Fourier transformation. Now, basically, a transformation is an operation because of which one form is get converted into another form. Here, consider a function w equal to f of z is equal to u plus iv of a complex variable z equal to x plus iy. Thus, a point P with coordinates x and y in the z plane corresponds to another point P dash with coordinates u and v in the w plane. Thus, if we have w equal to fz equal to z square equal to x plus iy whole square is equal to, we have already seen real part u is x square minus y square and the imaginary part v is 2xy. The point P x equal to 1 y equal to 1 in the z plane will correspond to another point P dash u equal to 0 square u equal to 1 square minus 1 square that is 0 and v is equal to 2 into 1 into 1 that is 2 in the w plane. Hence, if we have a curve C on the z plane that will correspond to another curve C dash on the w plane. Thus, the function w equal to fz defines the mapping or transformation of z into w plane. Bilinear transformation. The transformation w equal to az plus b upon cz plus d, where a, b, c and d are complex constants, is known as a bilinear transformation. Now, w is expressed as a function of z. If we try to express z in terms of w, then the inverse transformation is going to be z equal to minus d times w plus b upon c times w minus a, and the inverse transformation is also bilinear. Further, we can write the initial bilinear transformation as w equal to a upon d times z plus b upon d divided by c upon d times z plus 1, and further w equal to, now ABC are capital letters, a times z plus b upon c times z plus 1. Thus, actually 3 constants are involved instead of 4. Hence, we need 3 conditions to determine a bilinear transformation. Let us discuss some problems on bilinear transformation. First problem, find the bilinear transformation which maps the points 0, minus 1 and I of the z plane onto the points 2, infinity, half times 5 plus I of the w plane. There are some different methods. In this session, we are going to discuss the simplest and quite logical method. Let the bilinear transformation be w equal to az plus b upon cz plus 1. We know that as we have to determine values of 3 constants uniquely, we must have 3 bits of information, and that is available with us. Z equal to 0 maps into w equal to 2. Therefore, let us put, therefore 2 equal to a times 0 plus b upon c times 0 plus 1, and that is equal to 0 plus b upon 0 plus 1, that is b equal to 2. So directly we are getting b is equal to 2. Second bit of information, z equal to minus 1 maps into w equal to infinity. Now, therefore, infinity equal to a times minus 1 plus b upon c times minus 1 plus 1, that is equal to minus a plus b, and divided by what? Now numerator divided by denominator, the ratio is equal to infinity. That means that the denominator must be 0, that is minus c plus 1 equal to 0. That means c must be equal to 1, but that is not enough. Along with this, the numerator should not be 0. Otherwise, it will be 0 by 0 form, indeterminate form, and further we have to make use of L'Hospital's rule. In that case, the entire ratio may have any value. So here C is equal to 1, along with that A is not equal to B. This is the information we are getting. The third combination, Z equal to I maps into W equal to half times 5 plus I. Therefore half times 5 plus I is equal to A times I plus B upon C times I plus 1. We already know B and C, so let us put their values. A times I plus 2 upon I plus 1. Let us simplify further. Therefore, ai plus 2 is equal to half times 5 plus I times I plus 1 is equal to half times multiplication 5i plus 5 plus I square plus 1, that is half times 5 plus I square is 4, 6i, that is 5i plus I, 6i here, and that is equal to 2 plus 3i, 2 plus 3i, left hand side is ai plus 2, so a must be equal to 3. Thus we have found a also. Let us write a equal to 3, b equal to 2, and c is equal to 1. And the bilinear transformation is w equal to az plus b upon cz plus d, that is 3z plus 2 upon z plus 1 is the required answer. And the beauty in such type of problems is that after completing that problem, we can check whether we are correct or not. Yes. Let us try to put z is equal to 0 in this. So we are getting w equal to 2 upon 1, that is 2. Yes. Let us put z is equal to minus 1. So numerator is finite quantity, denominator is 0, w equal to infinity. If we put z is equal to I, then we will have to simplify, that will be 3i plus 2 upon 1 plus I. So multiply both numerator and denominator by the conjugate of denominator, that is conjugate of 1 plus I, which is 1 minus I, and after simplification we are getting w is equal to half times 5 plus I. Another problem, find the bilinear transformation which maps the points minus 1, 1, 0 of the w plane onto the points 0, I, 3i of the w plane. Solution, let the bilinear transformation be w equal to az plus b upon cz plus 1. Firstly, we are given z equal to minus 1 maps into w equal to 0. Therefore, 0 is equal to a times minus 1 plus b, that is minus a plus b, upon c times minus 1 plus 1, that is minus c plus 1. So, the ratio is 0, therefore, numerator must be 0 and denominator is not 0. That is a is equal to b and c is not equal to 1. Another bit, Z is equal to 1 maps into W equal to I. Therefore I equal to A times 1 plus B upon C times 1 plus 1. Therefore I times C plus 1 is equal to A plus I, A plus B, and therefore I times C plus 1 is equal to, we know A equal to B, so that is equal to 2A. We cannot go further, so let us keep and let us concentrate on the remaining bit of information. Z equal to 0 maps into W equal to 3I. Therefore 3I equal to A into 0 plus B upon C into 0 plus 1, that is 0 plus B upon 1. Therefore P equal to 3I. Also A will be equal to 3I. Okay. Still we do not know exact A, B. So let us make use of the previous equation we had got. We are writing here once again. I times C plus 1 equal to 6I, and therefore here C plus 1 equal to 6, and therefore C is equal to 5. Thus here W equal to AZ plus B upon CZ plus D, that is 3I times Z plus 3I upon 5Z plus 1. Therefore W equal to 3I my times Z plus 1 upon 5Z plus 1 is the bilinear transformation. Again you can quickly check. Z is equal to minus 1, W becomes 0. Z is equal to 1, so it will be 3I into 2, that is 6I upon 6, so W will be equal to I. And if we put Z is equal to 0, then that will be 3I. So very easy. One more problem of the same type. Find the bilinear transformation which maps the points 0, -1 and infinity of the W plane onto the points -1, -2, -I and I of the W plane. Let the bilinear transformation be W equal to AZ plus B upon CZ plus 1. W equal to 0 maps in, sorry, Z equal to 0 maps into W equal to -1. Therefore -1 equal to A times 0 plus B upon C times 0 plus 1, that is B is equal to -1. Z equal to -1 maps into W equal to -2 I. Therefore -2 I is equal to A times -1 plus B upon C times -1 plus 1. So let us put B is equal to -1 here, and we will be getting -2 I is equal to minus A -1 upon minus C plus 1. Therefore, so multiply throughout by -1, and we will be getting 2 plus I times 1 minus C is equal to A plus 1. Z equal to infinity maps into W equal to I. Therefore, we will have to revise this equation, because if we straight away put Z equal to infinity, we will be getting infinity upon infinity form. So we modify this formula. We divide numerator and denominator by Z, and we are getting W. W is equal to I equal to, here AZ plus B upon Z, CZ plus 1 can be written as A plus B by Z upon C plus 1 by Z, and we know B by Z is equal to 0, 1 by Z is also 0, that is A upon C, and thus there A equal to I times C. Therefore, 2 plus I into 1 minus C is equal to A plus 1 becomes 2 plus I times 1 minus C is equal to IC plus 1. Therefore, 2 minus 2C plus I minus IC is equal to IC plus 1. And after simplification, this is 1 plus I is equal to 2C plus 2IC. Therefore, 1 plus I is equal to 2C times 1 plus I, and therefore C is equal to half and A is equal to I times half. Thus, we have obtained A is equal to I by 2, B is equal to minus 1, and C is equal to half. Therefore, W equal to AZ plus B upon CZ plus 1 becomes I by 2 times Z minus 1 upon 1 by 2 times Z plus 1, that is IZ minus 2 upon Z plus 2 is the bilinear transformation. Let us discuss some another type of problems on transformation. Already we have discussed three problems on bilinear transformation. Show that the map W equal to 2Z plus 3 upon Z minus 4 transforms the circle x square plus y square minus 4x equal to 0 into the straight line 4u plus 3 is equal to 0. Now W equal to Fz is equal to u plus iv, and that is given as 2z plus 3 upon z minus 4. Therefore, u plus iv is equal to 2 times x plus iy plus 3 upon x plus iy minus 4, and that is equal to 2x plus 3 plus I times 2y upon x minus 4 plus I times y, and that is equal to, so let us multiply numerator and denominator by the conjugate of this, that is x minus 4 minus iy, and let us simplify here. So we'll be getting u plus iv is equal to 2x plus 3 times x minus 4 minus I square 2y square, that is plus 2y square, divided by x minus 4 bracket square minus I square y square means plus y square, plus I times 2 times x minus 4 times y minus 2x plus 3 times y, divided by the same denominator x minus 4 square plus y square. Now equating the real parts, because see, in the problem there is 4u plus 3, so we need only u. So let us equate the real parts. U is equal to 2x plus 3 times x minus 4 plus 2y square upon x minus 4 whole square plus y square. Let us simplify. That is 2x square plus 2y square minus 5x. Yes. So minus 8x plus 3x is minus 5x and minus 12. Divided by x square plus y square minus 8x plus 16. Just now we saw equation involves 4u plus 3, so that is equal to 4 times value of u plus 3. Let us simplify. So this is the LCM, and 4 times this expression plus 3 times LCM. Let us simplify. Therefore, 4u plus 3 is equal to 8x square plus 8y square minus 20x minus 48 plus 3x square plus 3y square minus 24x plus 48 divided by x square plus y square minus 8x plus 16, and therefore 4u plus 3 equal to, let us simplify the numerator. 8x square plus 3x square is 11x square. Similarly, 8y square plus 3y square is equal to 11y square minus 20x minus 24x is minus 44x, minus 48 plus 48 cancels, divided by x square plus y square minus 8x plus 16. Now, considering 4u plus 3 is equal to 0, we must have numerator equal to 0. Therefore, divide throughout by 11, x square plus y square minus 4x equal to 0. That is x minus 2 bracket square plus y minus 0 square. Already we had only y square is taken care of here, and here x square minus 4x. But we have written x square minus 4x plus 4. So let us add 4 at right hand side also. So this is equation of a circle. In the z plane, we center at x equal to 0, sorry, x equal to 2, y equal to 0, and radius is equal to 2. And we were asked, yes, finally we got the required result. Another problem, find the image of the circle modulus of z minus 1 is equal to 1 in the complex plane under the transformation w equal to 1 by z. Now w equal to 1 by z, therefore z equal to 1 by w. Therefore the given circle is modulus of z minus 1 is equal to 1 becomes modulus of 1 upon w minus 1 is equal to 1. That is modulus of 1 minus w upon w is equal to 1. That is modulus of 1 minus w equal to modulus of w. So absolutely no problem. For our convenience, we are saying this is modulus of w minus 1 is equal to modulus of w. We know w equal to u plus iv. So modulus of u plus iv minus 1 is equal to modulus of u plus iv. And this is modulus of u minus 1 plus iv is equal to modulus of u plus iv. Therefore, square root of u minus 1 square plus v square is equal to square root of u square plus v square. Therefore, u minus 1 whole square plus v square equal to u square plus v square. Let us simplify. U square minus 2u plus 1 plus v square equal to u square plus v square. U square plus v square cancels. Minus 2u plus 1 equal to 0. That is 2u minus 1 equal to 0. This is a straight line in the w plane. U equal to half. That means it is going to parallel to the v axis. So here we can understand that in the complex plane we had a circle in the z plane, and under that transformation we are getting a straight line in the w plane. Let us discuss one more problem. Find the map of the straight line y equal to x under the transformation w equal to z minus 1 upon z plus 1. We have w equal to z minus 1 upon z plus 1. Therefore, wz plus w equal to z minus 1. Because, see, w is expressed in terms of z and the transformation is given y equal to x. So, we want z in terms of w. Let us simplify. Therefore, 1 plus w equal to z minus wz. Therefore, 1 plus w equal to z times 1 minus w, and thus z equal to 1 plus w upon 1 minus w. So, as we are given w in terms of z, we have obtained the inverse transformation w in terms z in terms of w. Already we have seen both the inverse and the original. If first transformation is bilinear, then the inverse transformation is also bilinear. This is one illustration. Now let us put w equal to u plus iv. Therefore z equal to 1 plus u plus iv upon 1 minus u plus iv. Therefore z equal to 1 plus u plus iv upon 1 minus u minus iv. Let us simplify. For that, multiply both numerator and denominator by the conjugate of this denominator. Okay. So after simplification, we are getting z equal to 1 plus u times 1 minus u minus I square v square, that sorry, plus I square v square, that is minus v square, plus I times 1 plus u times v plus 1 minus u times v upon 1 minus u bracket square plus v square. And therefore x plus iy is equal to, here if we simplify, this is 1 minus u square minus v square plus I times is v plus uv plus v minus uv, that is uv cancels, we are remaining with 2v upon 1 minus u bracket square plus v square. So let us equate real and imaginary parts. X equal to 1 minus u square minus v square upon 1 minus u square plus v square, and y is equal to 2v upon 1 minus u square plus v square. Thus the map of the straight line y equal to x under the transformation is, as x and y both have the same denominator, numerator must also be the same. 1 minus u square minus v square is equal to 2v. Therefore, u square plus v square plus 2v is equal to 1. Further, we can write this as u square plus v square plus 2v plus 1 is equal to 1 plus 1, which is a circle in the w or uv plane with center u equal to 0, v equal to minus 1, and radius is equal to square root of 2. Okay, thanks a lot.